Hey everyone, welcome back to another explainer. I'm super excited to jump into this today because we're tackling one of the most fascinating challenges in modern renewable energy. We're going to look right under the hood and simulate a complete solar photovoltaic inverter system, step by step, using PSIM software. If you've ever wondered exactly how the chaotic, totally unpredictable energy from the sun actually gets tamed and transformed into reliable power, well, you are definitely in the right place. Okay, let's dive into this. So here's our core engineering puzzle for today. How exactly do you take a fluctuating, temperamental 130 volts of raw solar energy and basically force it into becoming a rock-solid, unwavering 320 volts of direct current? I mean, it sounds kind of like magic, right? But it's literally just pure power electronics. We're going to solve this puzzle together by building out our circuit virtually, block by block. To solve this, we'll follow a clear roadmap. First, the solar voltage problem. Second, building the PV array. Third, the boost converter circuit. Fourth, controlling the power. Fifth, analyzing simulation results. And finally, real-world applications. All right, section 1, the solar voltage problem. You know, the reality of raw solar output is that it's completely at the mercy of the environment. A passing cloud, a random temperature spike, or just a shifting sun angle means your voltage and current are going to fluctuate wildly. But contrast that with modern DC loads. The equipment, the batteries, and the microgrids we rely on every day demand strict, stable, high-voltage power. They literally cannot handle that roller coaster. So we have to build a bridge between these two realities. Moving on to section 2, building the PV array. For this simulation, we're using a total of 6 solar panels, but we can't just wire them up randomly. We're using a very specific parallel series topology here. We take 2 panels and wire them in series. This stacks their voltage so we get a much higher electrical push. Then we take 3 of these 2-panel strings and connect them in parallel. Why? Well, because parallel connections combine the current capacity. This exact 2x3 configuration gives us an overall target output of around 130 volts of direct current to act as our baseline input. But we have to set the ground rules for our PSM software. We're modeling these panels operating at their maximum power point under standard test conditions. That essentially means we're telling the simulation to assume absolutely perfect sunlight, 1,000 watts per square meter of solar energy irradiance, and a perfect operating temperature of 25 degrees Celsius. This gives us our theoretical maximum baseline of 130 volts to actually work with. Which brings us to section 3, the boost converter circuit. Okay, so our main goal here is to step up that 130 volts DC to a tightly regulated 320 volts DC. Think of it using a water pressure analogy. Our solar panels are basically giving us a wide, slow-moving river of water. It has energy, sure, but the pressure is just too low, only 130 volts. We need to blast that water out of a high-pressure hose at 320 volts. To do this, we don't just squeeze the pipe, we build an electronic pump that rapidly builds up pressure and releases it over and over again. That pump is our boost converter. And here's how that pump actually does its thing. It's a rapid 2-part heartbeat using high-speed MOSFET switch, an inductor, a diode, and a capacitor. Step 1. The switch turns on. Power flows from the solar panels right into the inductor coil. But instead of flowing through the circuit, the inductor traps that energy, storing it as magnetic field. It's kind of like pulling back a slingshot. Step 2. The switch turns off. That magnetic field rapidly collapses, acting like a second battery in series with the solar panels. This combined high-pressure energy shoots through diode and fills up our output capacitor. Pull back the slingshot. Release. Pull back. Release. All right, section 4, controlling the power. The actual brain of this whole operation is the PI controller. That stands for proportional integral controller. Because remember, solar energy fluctuates. If a cloud blocks the sun, our 130 volts drops, which means our 320 volt output will drop unless the system adapts. The PI controller creates this amazing closed-loop feedback system. It constantly looks at the actual output voltage, compares it to our desired 320-volt target, and calculates the error. It's just constantly doing the math in real time to figure out exactly how hard our boost converter pump needs to work right now to maintain total stability. So, the PI controller knows exactly what needs to happen, but it needs a way to actually talk to our high-speed MOSFET switch. And that language? That's PWM, or pulse width modulation. The controller generates a signal that tells the switch exactly how long to stay open and how long to stay closed. We call this the duty cycle. If the output voltage starts to dip, the PWM signal widens the pulse, keeping the switch on just a fraction longer to store a little more magnetic energy in that inductor. Now, the switching frequency is where the magic really happens, 25 kilohertz. That PWM signal isn't just flicking the switch on and off a couple times a second. It is literally opening and closing that gate 25,000 times every single second. This massive frequency is exactly why the gate controller can make such microscopic, instantaneous adjustments to maintain an incredibly stable 320-volt output, regardless of whatever the sun happens to be doing outside. Let's dive into Section 5, Analyzing Simulation Results. First up, let's look at the exact component specs we dialed in to make this happen. We've got our 130-volt input, aiming for that 320-volt output. But look closely at the inductor-capacitor filter, or the LC filter. To handle a violently fast switching environment of 25,000 times a second, we precisely sized our series inductor at 2.208 millihenries and our high-voltage output capacitor at 22.6 microfarads. This LC filter is our shock absorber. Let's see how it actually performs. When we analyze the inductor current, we see exactly what we'd expect. This continuous, jagged ripple waveform. That's just the chaotic, high-frequency noise of our pump charging and discharging 25,000 times a second. But thanks to our perfectly tuned 22.6 microfarad capacitor, that jagged energy is completely smoothed out at the output. The result? A flat, perfectly stable, beautiful line sitting exactly at 320 volts with negligible ripple. The filter works flawlessly. If we kind of zoom out and look at the system over time, the simulation shows us something else that's super important. When you first fire up a complex power electronics circuit, you get these startup transients, essentially momentary electrical blips and spikes as the inductor charges up and the PI controller gets its bearings. But as you'll see, both the input and output voltages stabilize incredibly fast. It rapidly locks right into a steady-state power delivery, ensuring that whatever sensitive equipment is drawing that 320 volts is totally protected. Finally, Section 6, Real-World Applications. You are literally looking at the backbone of our clean energy infrastructure. This specific boost converter topology, with its high-frequency PWM switching and that clever PI control loop, is absolutely essential for standalone off-grid solar systems. It's what powers modern DC microgrids for remote communities. It's the exact mechanism used in high-capacity battery charging setups. And, maybe most importantly, it acts as the vital front-end stage for grid-tied solar inverters. Before you can ever send solar power out to the city grid, it has to be perfectly conditioned to this exact high-voltage DC standard. Which leaves us with this final thought. We've successfully taken fluctuating solar power and forged it into a flawless, stable 320 volts of direct current. But the power grid in your house doesn't run on direct current, right? It runs on alternating current. So what exactly is the next step for integrating this 320-volt DC power into a dynamic, oscillating AC grid? How do we build the inverter bridge to make that jump? Think about that puzzle for a bit. Thank you so much for joining me on this explainer, and keep questioning how our world is powered.